Somebody asked about diamond versus carbon. Since they both have a similar crystalline structure, is there some reason why that we would prefer one or the other? And does this structure give us some way of using both in kind of the same way? That's actually a really good question. It turns out that the lattice structure in and of itself has some effect, particularly for the way we use diamond. But that's not really sort of the important part, or the important distinction. The important distinction is the number of electrons that the atom has and how those electrons are bound to the nucleus, and the number of protons and neutrons in the nucleus itself. Mm-hmm. So with carbon, for example, the most common carbon isotope is carbon-12, right?
Yeah, stable isotope is carbon-12.
Okay. Mm-hmm. But carbon-13 also exists.
Mm-hmm. Yeah, and 14 exists. Right.
Mm-hmm. And 13 has a nuclear spin. Mm-hmm. So the nucleus, it follows the same essential rules of quantum mechanics as the electrons and the photons do that we've been talking about sort of otherwise. But the nucleus itself is actually a much more complex structure. So the rules themselves behave in sort of complex ways. But that means that some nuclei of some kinds of atoms can actually be used to hold a qubit in and of itself. And so with carbon-13, we can actually store a single qubit inside the nucleus itself. Although getting that qubit data value into the nucleus and out of it's actually hard. We'll see that actually later on when we talk about hardware in week 4. Writing data into the nucleus and then taking it out, it's hard because it's actually pretty well isolated, because the electrons that are orbiting around the nucleus actually shield it from the other things that are going on. So carbon's actually useful in that sense. Here at our campus, the Keio University Yagami campus, where we are right now, our professor Kohei Ito, who you'll also meet in week 4, his laboratory actually works on this kind of isotopic control primarily for silicon. And so for silicon, the most common isotope is silicon-28. But if you control the amount of silicon-29 in a system, you can actually potentially use the spin of a silicon-29 atom as a qubit as well. So they're both usable. The characteristics are different in terms of the energy or the wavelengths you have to deal with things. The carbon structure that we often see in what we call the NV diamond form, the nitrogen vacancy form, where we actually pull out one of the carbon atoms and leave just sort of a hole in the lattice and put in a nitrogen atom instead. That allows us to operate at essentially optical wavelengths. So that's actually sort of a convenient physical platform to work in, but then, dealing with the materials for diamonds is actually harder in some ways. Whereas the processing technology for silicon is very well understood. So both are possible. The characteristics are kind of different, and so the ways you would use them are pretty different too. Any other comments?
No.
Nope. Okay.